In the first place, to thank Ufko for inviting me also this year. Some kind of traditional meeting, and it's always very nice to meet in this occasion and to present something new. And in this case, I took up something about our work on mitochondrial calcium. And to start my presentation, I thought to invite you to read the famous sentence of Galileo, since we are in this historical place, also for people coming from abroad. Everybody knows that Galileo was professor in Padova 400 years ago, and I think that one of the most important legacies of Galileo is the invitation to measure, not to use mathematics, to use numbers in studying astronomy. Maybe astronomy was the most interesting field for Galileo, but also for biology and medicine. Actually, for now, our time can be something rather obvious, but at this time, at the time of Galileo, was very controversial issue. And Galileo had long discussion with a friend, also professor in Padova, Cesare Cremonini. Maybe for the young people, for the Italian young people, Cesare Cremonini looks like the name for a singer. But it's just the same name. Cesare Cremonini was professor of philosophy in this university in the time of Galileo. They know each other, they were also friends, but they had long discussions, public discussions about just this point. Cesare Cremonini thought that quantification was completely useless. Quality was the only interesting aspect of phenomena, and in this way followed Aristotle. On the other hand, Galileo, supporting the importance of measurement, of number, of mathematical approach, was in a way a follower of another Greek philosopher, Pythagoras. And I feel that, all the modern science is a bit on the line of Galileo and Pythagoras more than on the line of Cremonini and Aristotle. Well, going now to the mitochondria, just reasoning in this way, I can say that I'm not satisfied by the knowledge acquired in all these years about the beautiful molecular machine which allow to calcium to enter in the mitochondria following the MCU, the mitochondrial calcium unipotent and all the other protein relate and leaving the mitochondria through the sodium calcium exchange. It's very important what we know about this, but it's not enough. It's necessary to know how much calcium can enter, can be accumulated in the mitochondria, and at which speed it can enter or leave the mitochondria. Actually, the first measurement in this level were performed long ago, something like 60 years ago, using isolated mitochondria, isolated from the rat kidney, in what cases, rat kidney cells, isolated mitochondria, to different groups, more or less in the same time, published two papers showing the same thing. On one end, Washington and his co-workers, and the other end, maybe even more known named Luca, showed that mitochondria isolated from this cell were able to accumulate very large amount of radioactive calcium. This result was very impressive at the point that people started to think that most of the calcium inside the cells was accumulated, was stored inside the mitochondria. Of course, this was an evolution, and this aspect was put a little aside, but never disappeared, and actually, more recently has acquired a very relevant interest. Of course, this was a very special preparation, isolated mitochondria, so it's not sufficient to give an answer to physiological question. And the physiological question, the question interesting for the physiologists about calcium and mitochondria, are mainly two. First question is about if this calcium taken up by the mitochondria is sufficient to activate those enzymatic activity which are calcium dependent. That was shown later on, not in the 60s but in the 80s, by Dinton and other biochemists. There are three hydrogenase, pyruvate hydrogenase, isocitrate dehydragenase and oxygluteinate dehydragenase, which are activated by calcium. So the calcium which is taken up by the mitochondria is sufficient to control, to activate this dehydragenase or not. And second question, the calcium taken up and also released by the mitochondria is relevant for the control of the cytosolic calcium. Cytosolic calcium which can then control other functions like secretion in secretory cell or contraction in muscle cell. And since I am interested in skeletal muscle fibers, these two questions must be put in the context of skeletal muscle fibers. The context which is characterized by very large changes and fast changes in cytosolic calcium. To activate the contraction and then produce relaxation, enormous amount of calcium must move from sarcoplasmic reticulum to cytosol and vice versa. Other important feature for the skeletal muscle fiber, this on the metabolic side, is the change in ATP consumption. ATP consumption can increase 100 times from rest to contraction, and this requires the mitochondria to be able to produce, just using those metabolic machinery, to produce comparable amount of ATP. To answer the question, several tools have been developed through the years to answer my two initial questions. Several tools which are probes, indicators which can measure and tell us how much calcium is present in the mitochondria. These tools can be divided into two groups, fluorescent chemical dyes, and among them the most popular, the most important is rod 2. And the second group, the second family, is proteins, fluorescent proteins, which are able to change their fluorescence binding calcium. There are several groups, several types of this. I just listed some of them. Equine, which historically is the first, Pericam, Chameleon, Zicam. Since we are in Padova, we are not only proud of Galileo, we are also proud of something else more recent. It was in Padova that people could, our colleagues, Giulio Puzzano and Rosario Rizzuto, about 30 years ago, were able to do the first measurement of calcium concentration in mitochondria of living cells. To this end, they developed a modification of equine. Equine is a natural protein present in jellyfish, fluorescent protein. They modified equine, attaching a target peptide, which is a part of the subunit A of COX, target peptide which drives the equine inside the mitochondria. So the equine localized inside the mitochondria can show how change the calcium inside the mitochondria. This was published in Nature in 1992, and immediately later on was also applied on muscle tissue. And in 1997, again in the lab of Giulio Puzzano and Rosario Rizzuto, the calcium inside the mitochondria was measured in myotubes. Myotubes are not really skeletal muscle fibers, are some cell on the way to become skeletal muscle fibers. So, for example, if you look at the distribution of the mitochondria and the equal inside the mitochondria, you don't see a well-organized pattern. You see that just many dots which corresponds to mitochondria sparsely distributed in the myotubes, and also the sarcoplasmic reticulum, which is the source of calcium in these myotubes, is not as organized as in the skeletal adult muscle fibers. Anyway, they were able to measure the calcium in the mitochondria and show, very important, summarize here some results, show that the basal level in resting condition is very low. It's below the micromolar concentration in the other row, 100, 200 nanomolar. But during calcium release, either induced chemically with caffeine or electrically depolarizing the membrane of potassium chloride, the concentration in the mitochondria can go up to several micromoles. So then in this condition, in this living cell, in this living muscle cell, it's possible to get large variation of the calcium inside the mitochondria. In adult skeletal muscle fiber, the first measurements were performed at Karolinska in Stockholm by Jan Lennegan and the time young co-worker Håkan Westerlund and Gosson, and you see some measurement. They use a chemical line. They use NOD2. They measure the change of calcium concentration in the mitochondria with NOD2 in a sequence of in a series of short tetani, and they observe an accumulation. So in this diagram we see on a time basis a phase, initial phases, lasting few minutes, during which there is this repeated tetanic stimulation. The fluorescence of NOD2 increases, indicating the accumulation of calcium in the mitochondria. Then at this dotted line, the stimulation ends, the skeletal muscle fiber is relaxed, but the concentration of calcium in the mitochondria is still high and declines very slowly. This is also an important point. We go back again to Padova. A few years later, 2004, again in the lab of Tullio Cozzano, using a chameleon, calcium was measured in the mitochondria in skeletal muscle fiber in a living mouse. Living mouse put under a 2-photon microscope. In this case, the probe used was a chameleon. How do we go back quickly? Just after the slide. What is a chameleon? Chameleon is a protein, fluorescent protein, which can, using a target peptide, again the same target peptide, the fragment of the unit 8 of Cox, can go to the mitochondria and indicate the variation of the calcium inside the mitochondria. Actually, they use two different chameleons. One chameleon, YC2, localized in the cytosol, so measuring calcium concentration in the cytosol, and one localized in the mitochondria. Also indicated, in this case, repeated tetanic stimulation, which are indicated by these short bars, black bars. So in the cytosol stimulation, calcium goes up and then down to the basal level. Stimulation again, up and down. In the mitochondria, it's not in this way. In the mitochondria goes up and then goes down slowly. So then there is some kind of accumulation. The calcium remains slow, remains high during this repeated series of tetani. And this very likely is relevant for the metabolic control, for the biochemical enzyme, for the enzymes and biochemical activity of the mitochondria. What are the chameleon? The chameleon are protein designed, synthesized by our jet cell in San Diego. They are based mainly on calmodulin. Calmodulin can bind calcium and change its configuration. On both sides of calmodulin there are two fluorescent proteins, CFP and YFP. When calmodulin doesn't bind calcium, the two proteins, the two fluorescent proteins are far away from each other. On binding of calcium, the two fluorescent proteins come close to each other and threat appears. So the activation, the light emitted by one fluorophore can activate the emission of the other. So the change of the emission of light emission of YFP depends on the amount of calcium bound to this fragment, this component of calmodulin. There is in addition a fourth component, which is the target peptide. In this case, a target peptide for the mitochondria. There are several families of these chameleon with different sensitivity to calcium, different speed of reactions. YC, mentioned in the previous slides, is the first family, then follow D1, D2, D3, D4. Here we see the response to calcium of YC2, this line, And in green we see the response of D3. D3, chameleon, is what we started to use approximately 10 years ago in our lab. D3 chameleon targeted to the mitochondria, again with the same peptide of the COX-8 subunit is coded in a plasmid, so transfecting the plasmid in the muscle, we can get the expression of the chameleon. The chameleon is expressed at a sufficient amount about in 1 week, so after 1 week we can isolate, dissociate the single fibers, which will appear green because of the fluorescence, and green light, UV light, because of the fluorescence emitted by the chameleon. After dissociation, fibers are generally left for 1 night to culture, to touch on laminin and stabilize, and then we start the measurement using the FET, so activating one fluorophore with a light wavelength around 430 nanometers. The activation of this light produces emission fluorescence from the first fluorophore at around 480 nanometers. If the two fluorophores are close enough, if calcium is present, the second fluorophore YFP is activated and light is emitted at around 500, so in the green. The first question, important question, is the localization, but we don't see very much yet because of the light in the environment, maybe it's not so essential, but this is a segment of fiber, high magnification, antibodies against COM20, which is a protein of the outer mitochondrial membrane, to see where the mitochondria are. This is the fluorescence due to the chameleon. This is the merging, and you can imagine that they correspond rather well. So between green and red, we get some yellowish color. It was don't worry from the light.
Light, you don't know what.
I mean, we also tried in many different ways to be sure that was really localized in the mitochondria. Here, again, we stand with anti-COM20 antibody, and we make some scanning of the staining to see the correspondence of the bands green and red. Here we stand with the antibodies against the hyaluron receptor to see, in this case, the spatial relation between the localization of the chameleon and localization of the calcium release unit, where the hyaluron receptor is present. I mean, we can feel rather confident that it's in the right position. This is about the localization. We show that it's in the right position in the mitochondria. Second step, the calibration. We want to have a number. We don't want only to know that the calcium goes up. No, we want to know how much calcium is accumulated. So calibration, exposing fiber permeabilized, gently permeabilized with saponin and with a pH comparable to the pH of the matrix, so back on the alkaline side, exposing fibers at different calcium concentration and getting this sigmoid relation between calcium concentration and the ratio between the light emitted by YFP and the light emitted by CFP. This sigmoid curve can allow us to obtain from ratio between the two emitted light calcium concentration using this equation. For this equation, we use generally the simplified form. As you can see, there is a part of the equation which is where calcium depends on the ratio between YFP and CFP emission. And there is a part which is dependent on the first derivative of this. assuming that the first derivative is very low, very small, can be neglected, so we can use this simplified form, which is much more easy. And of course, it's an assumption that the changes in fluorescence are not very fast. Actually, are fast for a biological time scale, but not fast for a chemical time scale. Examples of what we can get from this. Here is an example of a fiber stimulated with a tetanic train of stimuli lasting 2 seconds and with a frequency of 60 Hz. 60 Hz for a mouse fiber is not producing a completely fused tetanus. It's more or less 50–60% of the maximal force. We measure in the cytosol with fuel. We measure in the mitochondria with chameleon, with a specific chameleon. In the cytosol, we see that we start the stimulation, calcium concentration goes up, oscillates because it's not a completely fused tetanus. We stop the stimulation, immediately goes down quickly, and then there is this tail, which is generally related with the activity of albumin, the slow release of calcium, which has been bound by albumin. Mitochondria gives a different shape. Increase during electrical stimulation, but increase much more slowly, and increase tending to reach a plateau, which actually, in my experience, we never to reach. I mean, it tends to some kind of asymptotic steady state, but never arrives to steady state, even prolonging the tetanus for several seconds. When we stop, there is a rather quick initial decline, and then a very slow exponential phase. Moving, using the suitable equation from calcium, from ratio to calcium, we can see something very similar for the cytosol and for something very similar as a shape for the cytosol, sorry, for the mitochondria. But something which I want to underline is not only the different shape we could be also seen here, but also the different level. In a mitochondria, the concentration is much higher than in the cytosol. So mitochondria can really accumulate calcium at concentration higher than the cytosol. Concentration which is generally above 1 micromolar, 1000 millimolar is 1 micromolar. So then we can answer our question. The first question was about if this calcium is sufficient to activate the dehydrogenase. I took the diagram for the original paper by Denton and co-worker in 1980. 1 micromolar is here, and it's definitely sufficient to activate at least 2 of the dehydrogenase we see here, pyruvate dehydrogenase and oxoglutaric dehydrogenase. So, the concentration reached in the matrix is sufficient to activate the dehydrogenase, to activate the metabolism. The second question was about the possibility to control, to modulate the cytosolic calcium. I go quickly to some calculation which are based on our measurement and also on the models published by Beller and Hollywood some years ago. In resting fiber, the total amount of calcium, assuming that the cytosol, the intercellular space is 1 liter, in 1 liter of fiber, intercellular space of fiber, there is something more than 1 millimolar calcium. This 1 millimolar calcium is mainly localized in the sarcoplasmic reticulum, where the concentration of free calcium is high, 500 micromoles concentration, 500 micromolar concentration. And the amount bound to calsequestrin is also very high. Calsequestrin can bind at this calcium concentration 20–25 times more calcium. The amount in the mitochondria is little, even if assuming, this is a very critical point anyway, that the buffer present in the calcium buffer in the mitochondria can bind 100 times more calcium compared to the free calcium. So if there is 100 nanomolar concentration of free calcium can be 10 micromolars of calcium bound to many possible buffers inside the mitochondria. Anyway, the amount is very little compared to the sarcoplasmic reticulum. In the cytosol also the concentration is very small. There is some calcium free, 100 nanomolar is the concentration, and some calcium bound to calmodulin, to ATP, to different possible buffer, organic and inorganic buffer of the calcium. Contraction, the time of contraction is associated to the movement of something like 500 micromoles amount per liter of intercellular space from sarcoplasmic reticulum to cytosol and mitochondria. 1 liter, imagine a very big fiber, 1 liter space volume, 500 millimolar of calcium lives in a repeated series of electrical stimuli, something like 300 micromoles with the first electrical pulse, and then lower amount because of the change of the ryanodine receptor permeability. Anyway, something like half millimolar of calcium leaves the sarcoplasmic reticulum and goes to the cytosol and to the mitochondria. To the cytosol finds two very powerful buffers, troponin C, which can be even completely saturated in a maximal tetanus, and parvalbumin, which is not completely saturated, never completely saturated, because has high affinity for magnesium also, but can bind a substantial amount of calcium. Then other calcium is bound to calmodulin, to ATP, and to other possible. Assuming that, as we have measured, that calcium in the mitochondria goes up to above 1 micromolar, and the buffer can keep 100 times more calcium, whereas the amount of total calcium of 7 micromoles in the mitochondria, assuming that this volume of intercellular space is 1 liter. So a very small amount is controlled by the mitochondria. Big amount goes in the cytosol. So the answer to the question, if the mitochondria with this little amount of calcium can affect this big amount, is rather gives to negative answer. So we can take the first conclusion that we are sure that mitochondria can accumulate quickly large amount of calcium, reach levels which are above concentration, which are above the concentration in the cytosol, the concentration, not the amount. The kinetic is very typical, very specific because of a slow decline, which allows the mitochondria to keep for a long time calcium. And very likely this is essential to maintain the activation of the metabolic machinery. Then the answer to the question about the ability of the mitochondria to control cytosolic calcium is apparently negative. But there are several important evidence against this last conclusion. I just mentioned 4, and then I stop my presentation. 4, the first goes back 20 years ago, more or less. Gillis, Belgian muscle physiologist, showed that in acute condition, blocking with ruthenium red, the calcium, very peculiar type of fibers of a mouse model of ALS, where there are segments of fiber with mitochondria completely depolarized. And they measure, during voltage length, the concentration of calcium in the cytosol, in the segments with mitochondria polarized, therefore able to take up calcium, and mitochondria depolarized, unable to take up calcium. The depolarization of the mitochondria produced an increase of about 15% of the amplitude of the transient. And this implies that mitochondria can remove, can take away from the cytosol 15% of the calcium released from the cytoplasmic reticulum. Third evidence from Padova. In 2011 was identified the molecule, the protein responsible of the uptake of calcium, the MCU. So it was possible also to produce overexpression of this, and overexpression, which makes the mitochondria more powerful, more able to accumulate calcium, produce a slight, small but significant decrease in the concentration of calcium in the cytosol, measured in fuel. Again, mitochondria seems to be able to control, to modulate calcium in the cytosol. The last evidence comes from my lab, work done with Marcus Andre, in a mouse where there was a genetic manipulation producing the knockout of DLP1. DLP1 is a small protein which is essential for the fission of the mitochondria. If we remove this protein, the mitochondria cannot divide anymore, so there are formation of big, enormous, gigantic mitochondria. In this condition, in the presence of these very big mitochondria, we could observe that the transient, the increase of calcium obtained with electrical stimulation is reduced where the LP1 has been knocked out compared to one time. This is, I think, is visible by eye in this example, but then here there are several measurements and statistics show that in spite of variability, there is a significant reduction. So again, since the mitochondria can take away, remove calcium from the cytosol. So, finally, second conclusion, pharmacological and genetic manipulation of the mitochondria gives evidence that mitochondria can modulate cytosolic calcium. But I must say that, in my opinion, the mechanism is not defined. I mean, we can give several possible explanations. I'm not able to see what is the right explanation. One possibility is that we underestimate the buffering capacity of the mitochondria. In my calculation, as in other calculation published by other workers in the field, we have assumed that the buffering capacity is 100 times, so the calcium free is only 1% of the total amount of calcium present in the mitochondria. Well, with this buffering capacity, definitely is not sufficient. Maybe 1,000 times would be sufficient. But this implies also that the flow for the MCU is 10 times bigger. So this is an interesting hypothesis and is worth to be developed. Second hypothesis that must be developed is if mitochondria, when modified, genetically modified, pharmacologically controlled blocked, can send some message to the sarcoplasmic reticulum, either to the release or to the uptake, either to the adenine receptor and the machinery for the calcium release unit, or to the sarcoplasmic reticulum, ATPase, and the removal machinery. I don't know what type of message, but some message which can modify the amount of calcium present in the cytosol. I close my presentation with an open question. I don't know if next year we can give an answer. We'll invite you again. Thank you for your attention.